Hello world, this is Craig. Rather than do the memory decoding for the 3 different memory cards in one video, I'm going to split that into 3 videos so that if you're interested in one card, you can just go to that video and watch that and not have to suffer through all the blah 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 of everything else. That being said, before I start the first card, which we're going to do the MOD8-4 first, before I start this one, we have to do a little bit of blah 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 on memory decoding and why we are interested in memory decoding. And I'll put a little note right here in the video that if you want to skip ahead to just the answer, you can do so. I'll put what time to skip to. But for right now, let's look at the memory decoding and what we're trying to do. If we think about our memory in the system being just a sequence of addresses, we have a 14-bit address. So these go from A0, A1, A2, all the way up to A13, which is our 14th address because we started at 0. And then we also have up here A14 and A15 that I'm going to crowd off here on the edge because the 8008 can only address 14 bits. So these are always going to be 0 for the 8008, and when we use the 8080, this is still actually 0 because we're going to make it so it's kind of universal and will work on either processor. So at any rate, we have these addresses from 0 to 13, and these start all the way at 0 all the way down across the border 0, and these just go all the way up to until they are all 1, 1, 1, 1, 1 across the board. Okay, and so that gives us a total of 16,000 addresses, because that's how high we can count with these 14 bits, is we can count from 0 up to the 16K with that many bits. So we have got 16K. What we want to do is we want to place these memory boards somewhere in that 16K so that when the processor goes out and it's looking for a memory location, it knows how to find it. And the way that this bus works is each board is responsible for identifying when it is being selected. So it comes down to selecting using these little jumpers or switches or however, or solder, however you configured your boards. It comes down to configuring those so that this board knows when it's being addressed. Now it's important that only one board is addressed at a time, because let's say that we accidentally picked our jumpers here so that these 2 boards had a little bit of overlap in memory. And so maybe, a couple of these chips were overlapped to a couple of these chips. What would happen is the processor would go out and it would request information from the memory, and that memory happens to be mapped to this chip at the same time it's mapped to that chip. Then both these chips would turn on at the same time, and their bus drivers would turn on at the same time, and they would both be putting information onto the bus. If that information happened to match, there probably wouldn't be much of a problem. But if that information is different, let's say it's logic 1 from these and logic 0 from these, now we have a bus contention situation where these guys are trying to drive the bus high, these guys are trying to drive the bus low, and they can both go into an overcurrent situation, particularly the ones that are trying to drive it high. So it's important when we're mapping our memory out that we make sure we don't have any overlaps. And of course, it's important that we understand how our memory is mapped, because when we're writing our program, we're going to reference all sorts of things. We're going to reference where our RAM is. We're going to reference where our program is in ROM. And so we kind of need to know where that is. Okay, so first we're going to do this, which is the 8-4 ROM. What we want to do is map this somewhere into our memory. And of all this memory, we need to have a little 2K block that is just dedicated to this card. So nobody else turns on except for this card anytime we're within that 2K block. That's what we mean by this memory mapping. Okay, let's look at what this card, what this board actually looks like. Okay, so this is the 8-4 ROM, and it uses the 1702A. 1702A is 1 byte wide. So each of these chips has all 8 bits to form a byte. And so anytime that we're looking at something on this board, we're only looking at one chip at a time. What that allows us to do is we don't have to populate the whole board to get all 8 bytes. That's in contrast with the RAM, where these are 1 bit per chip. So what that means is we have to have all 8 of one group populated in order to get all 8 of our bytes. So you see, these are 1-bit chips, and these are 1-byte chips. So that's a fundamental difference in that each of these chips holds the entire byte. Now, it's 1 byte wide, and it's 256 lines long. Okay, so each of these has 256 bytes because it's 1 byte wide and 256 bits or 256 addresses long. We have 8 of those on a board, and each of them is 1/4 of a K, so that means that there's 1 K in these 4 and 1 K in these 4. So this is a 2K memory board. So this memory card requires a 2K reserve in all of our memory. And we can see that on the schematic. Here, if we look at our schematic, we've got our 8 memory chips, and they're all just connected with their outputs in parallel. So one at a time, these are selected, and the data comes out of the chip and goes onto the bus. So this decoding is all about how do we select that chip. Let's go back and look at our addresses. We have A0. When we look at these addresses, we will typically not refer to them as individual addresses. We group these together, and we call this N0. We group these 3 together. We call that N1. These 2, 3-bit number. N3, N4, and N5. That's what we refer to with these addresses. Now, to just decode 1 chip, how many bits do we need? Well, we can count that up. This will decode 1, 2, 4, 8, 16, 32, 64, 128. Okay, so this bit right here has the ability, its value is 128 lines or 128 bits of this decoding. That means that if this is a 0, we have 128 in that, and if this is a 1, we have 128 in that. So the upshot is that everything from 0 to 7 is required in order to get our 256 lines. So that means that all of this is required inside to decode which line it is within that chip. Okay, so from address 0 to address 7, all of that is just decoding the line. Now we have 8 chips on this board. What we're going to do is use the next 3 bits in the address to decide which of these chips we're talking to. Okay, so we've got 3 bits, and coincidentally we can do with 3 individual bits, we can pick 8 different things. Okay, so what we've got is 3 addresses, and we want to pick 1 of 8. Okay, so please welcome the 74138 1 of 8 decoder. What does this look like? This is a chip. Specifically, it's this chip right here. What that chip does for us is it has 8 outputs numbered from output 0 to output 7. And fortunately for us, each of these outputs is active low. So you see there's a little inverter on the output of this. And only one of these outputs is selected at a time. So at any time, at most, one of these is going to be low. The way we pick which one is low is we have 3 address inputs, A3, A2, A1, or 210. But at any rate, these 3 addresses decode, and only one of these is going to be low at a time. So for example, if we put in 000, then output 0 is going to be low. If we put in a 0, 0, 1, then output 1. Output 1 is going to be low. We can see here from the truth table at any one time, only one of the outputs is low, at most. And I say at most because there's another way to turn off all of the outputs, or disable them, or make them all go high, and that is because this chip also has 3 enables. It's got enable 3, enable 2, and enable 1, and these operate a little bit differently in that enable 1 and enable 2 are active low, meaning that this line has to be low, and enable 3 is active high, so in order to get this chip to turn on, this has to be a 0, that has to be a 0, and that has to be a 1. So we first enable this chip by giving it a 1, 0, 0 on these 3 enable lines. Then we give it an address, and whichever this address picks, it selects one of these to go low, and it'll continue doing that until this is no longer enabled. Something here doesn't match up. This whole chip becomes disabled, and then all of these would go high, and then nothing out here would get selected. Fortunately for us, these go low to select the chip. And if we look at the 1702, or if we look at it on our schematic, we see that the chip select for the 1702 is low. So that makes it really convenient for us in that each of these basically just goes out and connects to the chip select on one of these chips on this card. And I've had to put for myself a little note up here that shows what order these are in. So this is the chip select 0, select 1, 2, 3, 4, 5, 6, chip select 7. So that's the order that these are selected. So really it's as simple as just connecting these 3 addresses up to the next 3 addresses that we wanted to use to control that. Okay, so what that means is that now this selects which chip selects which line. So all of this from address 0 to address 10 is done. That's taken care of. That's all committed. That's committed just to select which chip and which line within that chip. Unfortunately, we don't even have to make any of that decision. That's all hardwired. But now what we want to do is decide when is this whole board selected. Because once with those 11 bits from A0 to A10, we can pick any line on this entire board. But now we have to know when this whole board is selected compared to when this board, for example, is selected, or my RAM is selected, or anything else is selected. That's what we're going to use these 3 addresses for. We're going to use these addresses to determine when this whole board is selected. And fortunately for us, the 74138 has given us 3 inputs, and those 3 inputs have to be in a specific pattern for that chip to be enabled, and by that chip being enabled, we're then inferring that the entire board is enabled. So all we have to do is have our 3 addresses, 13, 12, and 11, have this pattern 1, 0, 0, and that board is selected. And we can see on the schematic where we have the addresses from A0 to A7 going onto the chip, and that just continues and goes on up through all of the chips. And then we have addresses 8, 9, and 10 that come into our 3 address selections on the 74138, A2, A1, A0, and in this it's a 3208, which is the same pinout and the same function as the 74138, which is just more available now. And then we can see our 8 outputs that go to the chip selects on the 8 individual pins of the 8 individual chips. Okay, so how are we going to connect these enables to our addresses? So here's our addresses. We have A13. We're going to bring that in, and we're going to have a jumper. Same thing. A12, bring it in and a jumper. A11, bring it in and a jumper. We have over here our jumpers for E3, E2, and E1. Okay. Now, there is one more little thing, and that is that before we go into E3, one of these we have to pick. It doesn't matter which one, but E3 is the most convenient to pick. We have to AND this with our MRE, which is our memory read enable. So our memory read enable will come from the processor, and that is basically when we gate things onto the bus and when we are ready to read the bus. So however we have decoded this board, we then have to use the memory read enable as a final override that enables this board only when the MRE pulse is high. So we're going to AND this with the MRE in order to get E3. And if you look on the schematic, this is actually double buffered, and so they NAND it and then go through another NAND to invert it back. But that's the same as just ANDing it. All right, we have to have the pattern 1, 0, 0 for this board to be enabled. So obviously over here, we're going to need the address, and we're going to need the inverse of those addresses if we want to be able to do any deselection. Okay, so we're going to call this A13. This is A13 bar, A12, A12 bar, A11, A11 bar. Now we're going to put jumpers in between either of these and E3, either of these and E2, and either of these and E1. We're going to configure those jumpers so that whatever our address is, we can match this 100 when we want this board to be selected. Well, that's just making a fairly simple truth table. All we have to do is say these are our addresses, A13, A12, A11, and we fill out this truth table. Now, one thing I'll point out is this is really convenient on this board because A11, 12, and 13 coincide with N4. They're just lined up exactly. N4 is A11, A12, and A13. So what that means is that this single digit alone in our split octal address determines when this whole board is selected, right? Because this is exactly coinciding with N4. And that doesn't always happen. That doesn't have to happen. It's just so that it happens in this one. And it's just really convenient because now N4 alone defines when this whole board is selected. So basically we can say N4 equals 0, 1, 2, 3, 4, 5, 6, 7. The output we're looking for, remember, is a 1, 0, 0. This is on E3, E2 bar, E1 bar. That's what we have to have in order to enable that. So if we want that to happen, we have to take, for this to select N4 equals 0, we have to select A13 bar, and then A12 and A11. For this guy, we would have to do A13 bar, A12, A11 bar, and the rest, and so forth. So that tells us which address we have to have, either straight address or the inverted address, in order to get N to be any number between 0 and 7. That's straightforward enough, but need to introduce another concept, which is opportunity for confusion. And that is on their schematics, instead of calling these A13 or A13 bar or whatever, they have called them as follows. They say A11 is equal to 11 bar, and so that means that A11 bar is equal to 11. A12 is equal to 12 bar, and so A12 bar is equal to 12. A13 is equal to 13, and so A13 bar is equal to 13 bar. So these are a little bit backwards. These are a little bit backwards from what we would originally expect. From the notation, So that simply means we need to remap these onto our board so that we match the silk screening that's on the board. And so our table then will turn into this. A 13 bar will become a 13 bar. A 12 will become a 12 bar. And a 11 will become 11 bar. 13 bar, 12 bar, 11, and so forth. We fill out the rest of this table, and it goes like this. All right, so if we want N4 equals 0, then we will pick on our jumpers for our three choices. This is E3, E2, E1. We will pick 13 bar, which is down there, 12 bar, which is down there, and 11 bar, which is down there. So here's the final answer. Let me go back to my black pen. If we want N5, N4, if we want this board to be addressed from 0, 0, 0, 0, 0, up until N4 changes, so up until 0, 7, 3, 7, 7, then we would pick this first row, 0, 0, 0, so a 13 bar, 12 bar, 11 bar. That's what I have on this. This is E3, it's connected to 13 bar, E2 is connected to 12 bar, and E1 is connected to 11 bar. Now my other card, this one, I want up at 0, 2, 0. Okay, so we want this to be at 0, 2, 0, 0, 0, 0, up to 0, 2, 7, 3, 7, 7. So if I want 2, then I would just pick 13 bar, 12, 11 bar. And this is my E3, it's connected to 13 bar. This is my E2, it's connected to 12. And this is my E1, and it's connected to 11 bar. So that's all shown in the table on the MOD8-4 ROM board jumper settings. We can see that we can pick any start address, and so that's the start address of 0, 0, 0, 0, 1, 0, 0, 2, 0, and so forth. And remembering that that address then goes from that start address, for example, 0, 1, 0, 0, 0, 0, all the way up to 0, 1, 7, 3, 7, 7, because that's reserving a 2K block. Okay, well that's it for decoding the MOD8-4 ROM board. It's going to be a little bit quicker to decode this one because we've already covered all the basics. We'll decode the MOD8-5, and then Charles, the exciting news is Charles has reproduced the MOD8-9, and he calls it the MOD8-9B because he had to make some little changes to it. The MOD8-9 has got a little bit of RAM, it's got a little bit of 1702A, then it has a little bit of 2716 EPROM capability also. So it's a nice flexible board. But the decoding on that one's a little bit more complicated. But I wanted to do this one first because it was kind of the most straightforward, and then in the next video we'll do the MOD8-5. Okay, that's it. Thanks for watching. Hope you enjoyed it, and if you have any questions, let me know below. Bye-bye.